So we have discussed up to here. So now we have to discuss the frequency spectrum of phase modulated signal. To discuss about the spectrum of phase modulated signal. So we know the time domain signal waveform in EM signal, phase modulated signal is like this. CT plus 5T. So this is the phase modulated waveform. Phase modulated waveform. You can see that this is a time domain signal, no? So normally waveform is a time domain signal. Okay. So you know this term. So this can be defined as Kp by Vm xt. Xt is the information signal or baseband signal. This is the baseband signal. And this Kp is phase sensitivity. And Vm is the maximum amplitude of this xt. Okay. So this is 5T. So now we have to find the spectrum of the signal, the spectrum of this waveform. So what we have to do is that we have our popular tool, that is Fourier transform. So we can apply Fourier transform to find the spectrum of this time domain signal. So here we have a time domain signal. Then we can apply Fourier transform. Then we can find the frequency domain signal. So this is the spectrum. No? This is the spectrum. Signal spectrum. So we have time domain signal XPMT. Okay. Then we have to apply Fourier transform to this time domain signal XPT. Okay. Then we will have a spectrum or frequency domain signal. We can denote it by capital X omega. Okay. And, this can be evaluated through the integral. You already know that. Minus infinity to plus infinity. Our signal, our modulated signal, our waveform, time domain signal. This is this one. Okay. So I will write it here. Cos omega ct plus 5t. This should be multiplied by e to the power minus j omega t. We have to integrate it with respect to t. We can apply the limits and find the spectrum, the time domain, the frequency domain signal. Okay, so you can see that. So if you're going to evaluate this integral, okay, so you can see that this is time domain signal. No, this is phi t is a time domain function. It's a time domain function. Okay, and this one also a time domain function. No, so you can see that one time domain function is inside another function. So this is a function of a function. Okay, so this is a function of a function. So if we try to evaluate this, okay, So if you going to evaluate it by hand, it will be very difficult. Okay, sometimes it is not possible. So sometimes you can have some software tool to evaluate this kind of complex integral. Okay, but sometimes this kind of integral may not have exist. Okay, so so it is very hard to it is very hard to implement and impossible to evaluate this kind of integral. Okay, so we have to do some modification here. So you can see that directly we can't evaluate this kind of signal integral. Okay, this is we can't directly evaluate. Okay, sometimes the integral may not exist. Okay, this may not exist. So we couldn't find the frequency domain signal. Okay, through this process. Okay, so what we have to do is that we have to simplify. We have to, however, simplify this integral. Okay, we have to simplify this integral using some assumption. Okay, we have to use some valid assumption, and we can try to reduce the complexity of this signal. Okay, so so already I think you know that here we are doing very popular assumption, that is narrowband assumption. Okay, narrowband assumption. Narrowband assumption. So narrowband assumption means normally narrowband assumption in most occasion, narrowband assumption is used to occasion to event such that the carrier frequency is very higher than the modulating frequency baseband signal. So but here it is not the same as I could understand. Okay, sometimes my understanding may be wrong. Okay, so however, if we look at this signal, if we look at our time domain signal, this signal is cos omega ct plus 5t, this signal. Okay, so you know that this terms we can write as like this, AP Vn xt. So this is our information signal. Okay, so you can see that you can see that if we change this, okay, if we change this, it will not, it is affected to the frequency, it is affected to the frequency, but but in narrowband assumption, based on phase modulation, we normally done this 5T. We assume this 5T is very less than 1. Okay, this is the narrowband assumption in phase modulation. Okay, in phase modulation, this is the narrowband assumption. Okay, This is the narrowband assumption in phase modulation. So you can see that to set this 5t very less than 1, we have to set this kp, modulation index. This is related with modulation index directly, but this is we called phase sensitivity. Okay. So we have to set this phase sensitivity, and we can make this, we can restrict the range of this 5t, okay, 5t very less than 1, okay, but we don't need to change the frequency of this signal, no, we no need to bother about the frequency of this signal, frequency of this modulated signal, okay. What we are changing is amplitude here, okay. Okay. So this 5t, changing this 5t, okay, I hope you got it, you can understand it. Changing this 5t is mainly depend on the amplitude of the signal, okay, of the signal. But amplitude normally we normalize, no, already you know that we already normalize. So normalize means the amplitude of the signal we divided from the maximum amplitude of the signal, so that we can normalize the amplitude of the signal, okay. So here the amplitude of the signal is normalized, okay. So so normally amplitude will lie on -1 and +1, normalized amplitude of the message signal, okay. So we can reduce, or we can lower this range by setting the kp, okay. If you use very low kp, then this range, this -1 to +1, actually this is not -1 to +1, it is changing this 5t. We have already learned that this 5t is changing from -5 to +5, okay. In phase modulation, this 5t should be within this -5 to +5, otherwise some distortion can be happen, okay. So then setting this kp value very less than the 1, okay, we can set this 5t in very low point, no. So we can do this, we can make this 5t very less than 1 by setting the kp, okay. So anyway, it is not related with I can't see any direct relationship between the frequency of modulating signal and this narrowband assumption, okay, this narrowband assumption, okay. But normally in most communication system, we are doing the narrowband assumption with respect to the modulating frequency and carrier frequency, okay. So that is what I want to tell you, okay. So anyway, we no need to much rely on this. I just tell the information, okay. So maybe my understanding may be wrong, okay. I don't know. Anyway, I couldn't see any direct relationship, okay. So if you can verify anything, Okay, you can see any relationship, you can tell me. Okay, so let's see, when we are doing this narrowband assumption, we will see what happened. Okay, so that is the important thing here. So if you are doing the narrowband assumption, so I will write the signal again. It will be like this: AC cos omega ct plus 5t. Okay, so in narrowband assumption, we assume that this 5t is very less than 1. Okay, so this 5t is a very low value and it is near to 0. Okay, so we can say that this 5t is limiting to 0. Okay, so that is our assumption. Okay, this is our assumption. Okay, so we will see what happened. Okay, so you know that we can write this identity, this expression, using this trigonometric identity. We have cos alpha, cos beta, minus sin alpha, sin beta. So we can use this fuel identity. Okay, and hope we have used this identity in many locations. So in the same manner, we can use this to simplify this further. Okay, so if I apply this identity to this signal, then I have XPM, the phase modulated signal. So here I can write this AC cos omega ct. Okay, then cos ut. Okay, and minus. So AC is there. AC sine omega ct sine 5t. Okay, so still we have a function of a function. Okay, so still we have a function of a function. So still we couldn't integrate this signal. If we try to find the Fourier series using this the Fourier transform pair, still we couldn't find the integral or Fourier transform. Okay, because we have a function of a function. Okay, so now we are going to do this narrowband assumption. So what is the assumption? So we see that we assume that phi t, this signal, is limiting to 0. Okay, so this is very less value, very small value. Phi t is very small value. So what happened? Okay, so you already know that cos 0 is equal to 1. No, cos 0 is equal to 1. So this phi t, when this phi t is limiting to 0, what happened cos phi t? This phi t is limiting to 0. Okay, so that means this cos phi t is limiting to 1. Correct? So this cos phi t is limiting to 1. Okay, so that is the one assumption. Okay, then secondly, okay, so cos term, this cos phi t, using the narrowband assumption, this cos phi t, we can eliminate this cos phi t terms, no? Okay, because this is very near to 1. Okay, so we can use this, we can eliminate this term. Okay, we can substitute 1 instead of this term. Okay, so let's see about this sine term. Okay, so here also you know that, okay, phi t is limiting to 0, okay, and you know that sine 0 Sine 0 is 0, no? Sine 0 is 0. Okay. So you know already that sine 0 is 0. So when 5t is limited to 0, that means sine 5t also limiting to 0, no? Sine 5t also limiting to 0. Now you can see that this 5t also near to 0. Okay. This 5t is also near to 0. So we can say that when 5t is limiting to 0, sine 5t is limiting to 5t. Okay. So sine 0, when 5t is limiting to 0, sine 5t is limiting to 0. Okay. Limiting to 0. And again, we know that this 5t is also limiting to 0. No? Okay. So this 5t also equal to very much equal to 0, and sine 5t is also very much equal to 0. So sine 5t is very much equal to 5t. We can say that, no? So we can use this assumption. So this sine terms also we can eliminate. But instead of this sine term, we have to apply 5t. We have to substitute 5t. Okay. Anyway, we can using this assumption, okay, this narrowband assumption, this one, and this one, we can eliminate the function of our function. No? So that is the advantage here. Okay. So if I rewrite this signal, okay, after the assumption, I can rewrite the signal as XPM T AC cos omega CT. Okay, so this cos 5t is 1. Okay, so it is 1 minus AC. Here, sine 5t is 5t, no? So we can write it as 5t and sine omega ct. So we can write this, correct? Okay. So you can see that here we don't have function of a function. Okay. We have one function, one time domain function, and we have a product signal. Okay. Two signal is multiplied. So that means we have a product signal. So we can somehow evaluate this product signal using Fourier transform. So this we can evaluate. Okay. So what we have to do is to find the spectrum. Okay. To find the spectrum of this narrowband phase modulated signal. Okay, now we can apply Fourier transform here. Okay, so I'm not going to apply the Fourier transform here because already we have done it at amplitude modulation. We have evaluated the Fourier transform of cos omega ct. Okay, and also we have evaluated the Fourier transform of this kind of signal. Okay, and we give a name that. Okay, that is modulation theory. No? Modulation theorem. Okay, so I directly use this knowledge to find the Fourier transform of this signal. Okay, I'm not going to evaluate it. Okay, so I think you can remember that we have done it. Okay, we have evaluated it. So that is why I'm not going to evaluate it here again. So cos omega ct. Okay, the Fourier transform of cos omega ct we can write as delta omega minus omega c plus delta omega plus omega c. Can you remember? Okay, so we can write like this. Okay, the Fourier transform of cos omega ct we can write like this. Okay, let me verify it. Yeah, okay, correct, no? Cos omega naught t we can write as delta omega minus omega naught plus delta omega plus omega naught. So we have already done this. Okay, so using the Euler formula and using linearity property and using the frequency shifting property, we can evaluate this. Okay, we have done this, so I'm not going to do it again. So uh, so we get this term, we get the Fourier transform of this term using this identity. Okay, using this Fourier transform pair, and this also we can find using the modulation theorem. So modulation theorem, I will write the equation here. Okay, so I hope you can remember this. That is why I verify this modulation theorem at the beginning of this modulation session. Okay, because we have to use it in many times. Okay, so modulation theorem, it is said that so here it is a product signal with sine terms, and also we have verified the product signal with the cos term. No, so here it is sine terms. So I will write the modulation theorem related to sine signal. Okay, so it is like this. Xt, if we have a signal xt sine omega ct, okay, we can find the Fourier, we can write the Fourier transform like this: minus j, okay, half x, okay, x means the Fourier transform of this xt, okay, x omega minus omega c, okay, this is omega c now, omega c plus half x omega plus omega c. Okay, so this is using the modulation theorem, we can write the Fourier transform of this signal like this. Okay, so if I verify this, this one, no, no, this is frequency convolution theorem. Yeah, this one, no, okay, this one. So you can see that this one. Okay, so j half x omega minus omega. Okay, so our equation is correct, no? Okay, so here minus, and here minus. Okay, so here it is minus, and here it is minus. Okay, so this is the Fourier transform of this term. Okay, so if we write the complete spectrum, okay, so that is the Fourier transform of x phase modulator signal. Okay. So let's denote it as omega. Okay, so we can write this as Here we have term AC cos omega CT. So cos omega CT Fourier transform is this one. Okay. So we can write it AC phi delta omega minus omega C and plus AC phi delta omega minus omega plus omega C omega C. So this term finish. Okay. Then we can write the Fourier transform of this signal, this term. Okay. Using this modulation theorem. Okay. So it will become, here it is minus J. I will write it. Okay. So minus J half. Okay. So here minus is also there. So that means minus minus, it will be plus. Okay. Plus J by 2. Okay. Plus J by 2. X omega minus omega C. So here minus minus plus, then again here it is minus, then it will be minus, no? Minus J by 2 X, no? Omega plus omega C. Okay. So this we have. Okay. So this is our complete spectrum. Okay. This is our complete spectrum. Okay. So normally this term, this plus term, this term and this term, these are imaginary terms. Okay. These are minus frequency. Okay. So these are imaginary terms. So normally when if we look the spectrum using a spectrum analyzer, this part we can't see. Okay. And we can see only this one and this one. Okay. In laboratory, you can verify that one. In spectrum analyzer, we can't use this minus frequency, and we can see only this frequency. Okay. If I write this complete signal, okay, if I draw the complete spectrum, it will look like this. Okay. So this is 0 terms. Okay. And this is omega. Okay. And you know that we have write it also with respect to f. Okay. Normal frequency. Okay, now we are write it respect to omega. Okay, but same graph, but sometimes these terms can be changed. Okay, so here we have first we will write this one, delta omega minus omega c. Also already you know that delta function is like that at 0. Okay, so with respect to omega. Okay, so omega minus omega naught means it shifted to here at omega naught. Okay. So here we have this kind of impulse. Okay, this term. Okay, then this one AC. So this is AC 5. Okay, and here AC 5 delta plus omega C. That means it is shifted to minus side. Okay, so this impulse is like this. Okay, and it is AC 5 volts. Okay, and if we write this one, you can see that this signal, it is omega minus omega c. That means it's shifted to here. Okay, we don't know the spectrum here. Okay, but anyway, it is centered in the omega c, no? Because it shifted with omega c. So you will get this kind of spectrum. Okay, for this term, still we don't know. And for this kind of signal, it is shifted to here, but it is minus, no? Then you will get like this. Okay. We will get like this spectrum. Okay. So this is the complete spectrum, but these terms we can't see this term using oscilloscope, sorry, spectrum analyzer. We can only see this. So normally, in many cases, we only consider this spectrum only. Okay. So this is the practical spectrum. Okay. So if I write the the plus frequency terms only, plus side only, okay, we get the phase modulated spectrum, phase modulated spectrum like this. Okay, we have capital X phase modulated spectrum. Okay, and we have these terms, this term and this term only. These terms and this term will be, we normally these two terms we normally not we don't consider. Okay, so we only consider this plus frequency term. Okay, so it is AC5, AC, sorry, AC means the amplitude of carrier signal. Okay, AC5 delta omega minus omega naught plus half J, okay, capital X omega minus omega, sorry, it's omega C, and here is also omega C. Okay, so this is a frequency spectrum. Okay, so this is the general spectrum. Okay, so you can write this in terms of F. Okay, so you know that this omega is equal to 5F. Okay, so you can write this in terms of F, but you can't directly apply to pi F here because this is inside the function. Okay, so you have to come it at the beginning. Okay, but the derivation is not much difference. Okay, the same procedure we have to follow. Okay, so yeah, it will look like, I think as I can remember, it's come 5 by 2 delta F minus FC plus J half X F minus FC like this. Okay. Yeah, this one, no? Okay, no? Phi is not there. Okay. So phi, this phi is not there. Okay, because when we are substitute this instead of omega. Okay, so sometimes this phi may be vanished here. Okay, so you have to come so we can't simply apply to phi f here, and we can't get out of this 2 phi. Okay, because this is a variable. Okay, so we have to uh, we have to uh, we have to follow the procedure. Okay, so anyway, if we write in terms of f, it will look like this. Okay, so this one and this one, the both are correct. Okay, this one also correct, and this are also the frequency domain signal. Okay, so if we move to our question now, so you can see that we have this our signal t cos omega ct xc. So we have a singleton modulation here. Okay, because one sinusoidal signal is there as a information signal. Okay, that means one tone is there. Okay, so this is sometimes this is called singleton modulation. Okay, singleton modulation. Because only one tone is there, sinusoidal, one sinusoidal signal, that means one tone. Okay, so one our information signal is one sinusoidal signal, sine signal. Okay, it is like this, nt is equal to am cos omega ct term, this kind of signal, okay, and so it is a sinusoidal signal, and one sine signal is there. One sine signal means one tone is there. Okay, so that means sometimes we called it as single tone modulation. Single tone modulation. Okay, so so if we have this kind of signal, okay, so this is our frequency spectrum. Okay, this is our frequency spectrum. I will use this because I am more familiar with this omega. Okay, so I will use this one, and all, of course you can use this one also. Okay, so if you use this one, you can see that here we have x omega minus omega c. Okay, x omega minus omega c. Okay, that means this x omega minus omega c means this x. Okay, this x represent the Fourier transform of this information signal. Okay, so this x represent the Fourier transform of this signal. Okay, and that signal should be shifted by omega c. Okay, so you can derive this term. Okay, you have to only derive these terms, no, because these terms already you know. Okay, so this information signal only affected to this signal, only affect to this signal, this part, this term. Okay, so you have to evaluate only this term to evaluate the frequency spectrum. Okay, so you can see that you have to evaluate this half j x omega minus omega naught. Okay, so this m or x omega minus omega naught means the Fourier transform of this message signal, and after getting the Fourier transform, it is shifted with omega c, time shifted with omega c. So you have to find this term. Okay, so if you find the Fourier transform of this signal, okay, now I am going to find this term. Okay, don't be confused. Okay, now I'm going to find this term because only this term we have to find. Okay, to find the Fourier spectrum, basically we have to evaluate this term and this term. Okay, and already this term is evaluated. No, we have constant value. It is not a constant value, but it is we can say it is a constant value. No, it is not changing with this information signal, but this part is only changing with the information signal. So I am going to evaluate this part only. Okay, so so for that I have to first evaluate the Fourier transform of this message signal. Okay, so it is a cos signal. Okay, so it is a cos signal, so already you know the Fourier transform of this signal. Okay, that is the, I will write the m also here, am, it is a constant, so I can get it out, and I have 5 delta omega minus omega naught. Here it is omega minus, here it is omega m. No, this is our modulating frequency, omega m. Okay, so here it is omega m. Okay, so here we have omega m. Okay, and I have plus am 5 omega plus omega m. Okay, so I have these two terms. If I evaluate the Fourier transform, it is a cosine signal. Okay, so I can use this identity. This one. Okay, so this one, Fourier transform of cos signal, this one. So I have used it here also. Okay. So I got this Fourier transform of this signal, and also I have to shift it with omega c. Okay, here it is omega c. So I have to shift this signal. Okay, then if I shift this signal, I will get this term. So it is here, it is x, but I will write it as m. Okay, because here the modulating frequency, modulating signal, we represented using m. Okay, so I will represent it capital M, the spectrum. So omega minus omega c, I have a m5 delta omega minus omega m, and this is shifted with omega c. So I have omega c plus a m5 omega plus omega m, and I have to shift it again omega c. Okay, so I have these two terms. No? Okay, so if I write the frequency domain signal for singleton modulated signal, okay. So if I write the frequency spectrum for singleton phase modulated signal, okay, I will have that is xc omega, okay, xp, sorry, phase modulated signal. So I have AC5. So here also I will only consider the plus value, okay, plus value. So only this term, okay, only this term I will consider AC5 delta omega minus omega c, right? Okay, and plus we have this terms. No, here also we have two terms, this one and this one. So if you write this again, okay, if you write this again, you have here omega minus omega m plus omega c, okay, you have this term. And if you get this omega plus, okay, now you have to get the both signal. No, here also we can write this as omega minus omega c minus omega m. Okay, so I have to write these two terms. The both the plus side shifted signal. Okay, so I write a m here a m 5 delta omega minus omega m plus omega c, okay, and also another term there, that is this half j, no, this term is also there. So I have to use here, I didn't use the half here, so here half should be here, and j also here, so j also should be here, and it is common to both signal, no? So here we have to use j half, okay, and plus, okay, plus j half m5, okay, delta, it is delta, okay, it is delta omega minus omega c minus omega m. Okay, so these terms I have. Okay, so if I draw the frequency spectrum, okay, so I draw the frequency spectrum here. Okay, so here this term I have, okay, it is impulse function shifted to omega c. Okay, so here it is omega c, and pulse function will look like this, AC5. Okay, and this terms omega minus omega m plus omega c. So here it is shifted to here omega plus omega c. So here it is omega c. If I take omega m value from this omega c, if this is omega m, then this point will be omega c plus omega m. No? So here I have one spectrum. Okay, this one. Okay, and it is a M5J2. Okay, and if I consider this term, it is omega minus omega c, omega minus omega c omega m. That means it is shifted to here, and the point should be omega c minus omega 1. So if I get the another value omega m here, so this point will be omega c minus omega m. No? So in this point also we have another spectrum like this, another peak like this. So this is the spectrum, the first side spectrum for Singleton phase modulated signal. Okay, and if you get the minus side, it will like this. I think, I hope it should be like this. Okay, so you can see it if you want. Okay, but for the answer, this will be enough. Okay, so so what you have to do is you can so you can apply this value here without a problem. Okay, so here to 520 to 5020. No? So this point is this you can see that omega is equal to 5f. Okay, so f is equal to omega by 2 5. Okay, and so you have instead of omega we can use this. Okay, no problem. So here we have to 5 10,000. Okay, and here this point we have to 5 10,000 minus to 500, and this point we have to 5 10,000 plus to 500. Okay, so this is our spectrum. Okay, in omega. Okay, I write it in omega. So this is equal to omega, no? So this I write it omega. I write it with respect to omega. Okay, so that also okay. This is the angular frequency, and this spectrum is also okay. Okay, this is angular frequency. So I hope you can find the spectrum of phase modulated signal in the case of narrowband signal, and also in Singleton modulation. Okay, so I hope now you can evaluate this kind of spectrum. So we will wind up. Okay.